Hello, everybody. Today I'm going to talk about the Jane Street robot baseball puzzle. Okay, this is the October 2025 puzzle, and my name is not on the leaderboard, but I did manage to solve it, but I had a mistake. So after looking at the solution and fixing my code, I got the correct solution. So I think it's worth to go over how I solved it. Um, so the Artificial Automaton Athletics Association is added again to compete with postseason baseball. They're developing a robot baseball competition. Games are composed of a series of independent at-bats in which the batter is trying to maximize expected score and the pitcher is trying to minimize expected score. An at-bat is a series of pitches with a running count of balls and strikes, both starting at zero. For each pitch, the pitcher decides whether to throw a ball or strike, and the batter decides whether to wait or swing. These decisions are made secretly and simultaneously. The results of these choices are as follows. If the pitcher throws a ball and the batter waits, the count of balls is incremented by 1. If the pitcher throws a strike and the batter waits, the count of strikes is incremented by 1. If the pitcher throws a ball and the batter swings, the count of strikes is again incremented by 1. If the pitcher throws a strike and the batter swings, with probability p, the batter hits a home run, and with probability 1 minus p, the count of strikes is incremented by 1. An at-bat ends when either the count of balls reaches 4, in which case the batter receives 1 point, the count of strikes reaches 3, in which case the batter receives 0 points. The batter hits a home run, in which case the batter receives 4 points. By varying the size of the strike zone, quad A can adjust the value of P. The probability of pitch strike that is swung at results in a home run. They have found that viewers are most excited by at-bats that reach a full count, that is, the at-bats that reach the state of 3 balls and 2 strikes. Let Q be the probability of at-bats reaching full count. Q is dependent on P. Assuming the batter and pitcher are both using optimal mixed strategies and quad A has chosen the P that maximizes Q, find this Q, the maximal probability at-bats reach full count, 10 decimal places. Okay, great. So now let me share my window capture. There we go. Okay, let me share this, and then let me go back here. Then delete this, delete, and create new board. And select the pen, and make sure I'm still recording. Fantastic. Okay, so let's look at this problem. So here we have the batter, and the batter can either wait or they can, let me see what the exact terminology is, swing, right? Those are the two choices, right? And I'm going to draw like a square matrix of the possibilities here, right? And then on this side, we have the pitcher, right? And the pitcher can either throw a ball, right? Or they can throw a strike. So again, going back to the problem, what happens if the pitcher throws a ball and the batter waits? Then balls is increased by 1, so balls plus 1. If it's a swing and a ball, then strikes plus 1, right? If it's a strike plus wait, then strike plus 1. And then if it's a swing and strike, then we go into this mini game, right, where with probability P, we get a home run, right? And with probability 1 minus P, right, we get strikes plus 1. So this game continues until, if balls is equal to 4, right, then this is 1 point for the batter. If strikes is equal to 3, then this is 0 points for the batter. And then if it's a home run at any point, right, then this is 4 points. This is like a really good outcome for the batter, right, and very bad for the pitcher, right? So let me just draw what a typical game would look like, right? So these number of balls and strikes is like it's like a state, right? So at the beginning of it, we started 0-0, right? And so this is kind of like dynamic programming, right? So suppose we hit a we hit this state, right? So the batter chooses to wait and the pitcher chooses to throw a ball. Then maybe we could go to this state instead. Or if one of the other ones happens, then we could go instead to 0-1, right? Where the first one is the number of balls and the second one is the number of strikes. So we can keep building this out, 0-2, and then 0-3. So at 0, 3, you know, the number of strikes is 3. So here this is like an exit condition, and then this is 0 points, right? And then again here for 1, 3, right? Going down, and then 2, 3, right? And then, you know, and then 3, 3 is also 0 points. And then on this side we have, you know, 4, 0. This is 1 point, 4, 1, 4, 2, and then 4, 3 doesn't exist, right? Because it's either you know, here, like that. So 2, 0, 3, 0, 1, 1, 2, 1, 3, 1, like this. So basically at any state you can move either to the right or down, and also at any state you can you have a chance to hit a home run, right? And you instantly win, and you win a lot, right? If you're the batter, right? So roughly this is what like the dynamic programming problem could look like, and you can imagine thinking about you know, you can like we can define this value function, which is what I eventually want to do. I want to define, you know, what is the batter payoff. What is the batter payoff at the current number of, you know, balls and strikes, right? So there's a couple easy ones here. Let me check. I'm still recording. Yes, there's a couple easy ones here, right? So at, you know, 4, 0, right? The batter payoff is 1 point, right? We've covered that. That's an ending condition. At 4, 1, at 4, 2, it's 1 point. And again, same with things 0, 3, 1, 3, 2, 3, 3, 3. However, it starts to get more complicated in these intermediate values, but you can see how like this is possibly a slightly dynamic programming problem. But regardless, I think I've skipped over the most interesting or the most crucial part of this whole thing, which is, you know, this sort of mixed Nash equilibrium. And what I mean by mixed Nash equilibrium, so I don't have the strongest background in this, but the way I think about it is that if I were the batter, in order to be as unpredictable as possible of an opponent, I'm going to have a probability. So first of all, I'm going to make my actions with random probability. I'm just going to, you know, with random probability do a weight or a swing, right? Now, this is not going to be 50-50, right? One of them could, depending on the value of p, but that's more complicated, but one of them could have a much greater reward or a greater chance of reward, because I also don't know what the pitcher is doing, right? And so, you know, I might weigh one more than the other. But the idea is, in order to remain truly unpredictable, I'm going to choose my probabilities such that the expected payoff of choosing either option 1 or option 2, either weighting or swinging, I'm hoping that the expected payoff is the same. Okay, and the same thing I'm going to say about the pitcher. In order to remain truly unpredictable as the pitcher, I'm going to weigh my probabilities such that the expected reward weighed by the probabilities of both of them is exactly the same, right? So I don't care ultimately which one I end up going with, depending on the probabilities, of course, because both of them will give me the exact same on average payoff. That's how I remain truly unpredictable, right? So let me write down that that conception, right? So in order to write that down, I'm going to say, as a batter, I'm going to swing with probability x. Weight with probability x and swing with probability 1 minus x. Because, you know, I have two choices, so x and 1 minus x. Okay, so then as a pitcher, I'm going to pitch a ball with probability y and a strike with probability 1 minus y. Right? Okay. Fantastic. So now, what I said about the batter is I really, truly, you know, don't care at all what my you know, which of these two choices I make. And in order to formalize it, I'm going to say the expected value of choosing this thing is going to be the expected value of choosing this thing. So here's the following equation I'm going to write. I have this function, batter payoff, and this is a recursive function that I try to define on this grid here with clear base cases. So I'm going to say that y times the batter payoff, I'll say BP, of balls plus 1, and then strikes, right, plus 1 minus y times BP of balls strikes plus 1 is equal to, right, is equal to y, yes, times BP times balls strikes plus 1, right, plus 1 minus y times, and then here's where it's slightly more complicated. With probability P, we hit a home run, and the payoff here is great, 4, right? But then with probability 1 minus P, it's BP times strikes plus 1, right? Plus 1. Fantastic. So, from this equation, actually, so these are actually, we actually know these values because we can, in order to calculate the batter payoff of this, we calculate the batter, we need to use this one and then this one, right? But then this one depends on this one, but this one we know what it is, right? And then this one, so this one depends on this one and this one, right? And then, this one depends on this one and this one, but these are known values, right? So what I'm trying to say is that this is something we can easily calculate recursively, right? Just that, right? Assuming that we know that, right, it's pretty easy to solve for y in this case, right? So, or for what the pitcher is on average going to do, assuming they follow their mixed Nash equilibrium where both of their payoffs are produce equal expected payoff. So let me go back to my code just to see what this could be, and the answer that I came up with is P times 4 minus P times S divided by, so this will be B minus S plus P times 4 minus P times S. Did I say P minus S? Yes. Okay. Where, B is the, this one, the balls, BP of balls plus 1 strikes, and then S, I just wrote in my code this way, BP balls strikes plus 1, right? So here we've found a value for y, and in order to calculate the expected, we haven't reached the batter payoff yet, right? In order to calculate the expected, expected batter payoff, all we do is, both of these are the same, so we can just evaluate probably the simpler one, right? So y times b, right, in this case, plus 1 minus y times s, right? So here's our return value for this function, right? So we have some base cases, of course. If it's equal to 4, then we return 1. If the strikes is 3, then we return 0. And however, if neither of those base cases are a thing, then we go through this calculation to find out y, and then we return this big thing, right? And actually, if you look at this, so I throughout this whole thing, right? Let me make sure I'm still recording. Yes, but it looks like it got stuck a tiny bit. Okay, there we go. Okay, fantastic. So you can see. Let me just walk through it. It looks like it stopped recording here, but you can see here that I wrote down the batter payoff, y, and then 1 minus y, and then here these two equations are the same, and I solved for y, and then here I returned the final, and here y times b plus 1 minus y times s, right? Fantastic. Okay, so if you notice here, this is symmetrical in terms of x and y, so I could easily just have drawn a circle around these two instead, like this. And then in this case, right, the equations are exactly the same, except instead of 4 here, it's a minus 4, right? So anywhere you see a 4 here, just replace it with minus 4, and that's how you'll get the pitcher payoff, right? And you can actually then later, it's easy to check. So the pitcher payoff, yeah, and then instead of returning 1 in this case, you'll return -1, right? And then so basically it's just the pitcher payoff is the exact negative. I mean, I wrote both just to check, but the pitcher payoff is as expected to be the exact negative of the batter payoff. Okay, so this is great. Now we know what the batter and the pitcher are doing in this mixed Nash equilibrium. They're both trying to win, to minimize or maximize the score, and they're both they have two choices, and they have some probability y and x that depend obviously on p, they depend on the current status, the current number of balls and strikes, and depending on that they make some decision about x and y, which is why we have to recalculate x and y every single time. It depends on the current state of the game, right? The number of balls and strikes. So for example, in the beginning, the batter, right, he might be way more happy to throw out swings, right, in order to potentially hit a home run. But if they're if they're close to winning by balls, or if they're close to strikes or something, maybe they'll play more conservatively. You can think of it in that way. So how their strategy might change over time. Fantastic. So, but this is not what the problem is about ultimately. So these two players, right, they're playing the game, but what we care about is this special state here, right? We care about this guy right here, 3-2. So apparently, according to the problem description, this is super exciting, right? Why is it super exciting? Because potentially the batter can win, right, and go to 4-2 and get 1 point, or the pitcher can win and go to 3-3 and the batter gets 0 points. So this is like the most exciting place. So, and this is what we truly care about, is finding the probability p that maximizes the probability of getting to this value. So for me, this is a pretty easy solution, or a pretty easy problem, now that we figured out what the batter and pitcher are doing, right? So I will define a new function called probability of reaching the good spot, right? Of the good spot. And this will be depending on p, right? I mean, this BP or whatever, this is also dependent on P, right? Because P is used a bunch here. P, again, being the probability of hitting the home run. So the probability of a good spot depends on P. Again, it depends on the current state, balls and strikes, right? So, so what is the probability, if you're at 4-0, what is the probability of hitting the good spot? It's actually 0, right? Because we have already finished the game, right? The batter has gotten 1 point, but we've never hit 3-2, right? Because we're at 4-0, we've never hit 3-2, right? So this is good for the batter, but for us it's bad because we care about maximizing the probability of reaching this state, right? So this is bad. 4-0 returns 0, 4-1 returns 0. And then we don't need to worry about 4-2, but 0-3 also returns 0, 1-3 returns 0, 2-3 returns 0. Okay, so and then 3-2 returns 1. So this is our good state, right? However, again, we need to find a recursive formulation for all of the other ones, right? That depends on a future game, right? So I think it's pretty easy. It's very similar, right? Here we have x, 1 minus x, and then y, 1 minus y. Let me make sure I'm still recording. I am not quite recording. Drat this. Okay. So here, the probability of a good spot depends on p, balls, and strikes, right? So here we have x, 1 minus x, 1, y, 1 minus y. So here, if it's an xy, right? So this will be, they hit the weight and ball, right? Then this will be equal to probability of good spot, where balls has increased by 1, right? So again, this recursive formulation, or dynamic programming formulation. Then this is again probability of good spot, where balls strikes plus 1, right? Plus 1. Then we have here probability good. This is also again balls strikes plus 1. And then finally here, right, with probability p we hit a home run. which ends the game instantly and doesn't allow us to go into this good spot. So this is actually 0. So p times 0, right? P times 0, which is not good, plus, right, 1 minus p times, the probability of ball strikes plus 1. Fantastic. Oh, and didn't record this as well. Okay, great. So you can see there I drew the square matrix. Fantastic. So finally, just to write this out, right? The probability. So we have some base cases, right? But for any other case, right, the probability of a good spot, given that we are currently at p balls and strikes, is equal to, right, x times y times this thing, right, times, I'll just say that thing, plus 1 minus x times y times this thing, right, plus, 1 minus, x times 1 minus y times this thing, plus, and then the p, this term is 0, right, plus 1 minus p times 1 minus x times 1 minus y plus this thing, right, where this is, let's say s, not plus, s, and then here this one's b. Okay, fantastic, and we are recording. So that pretty much just about solves the problem. Yeah, so basically the way I like to think about this problem is we're just passive observers. We have this batter and the pitcher, they're both trying to win, right? And then the only thing we can change is p, and we're hoping that we eventually that we pick the right p that has the probability of hitting this interesting state the most, right? And we found some base cases for that, and then x and y. And I should say also that it's pretty, now that we figured out what x and y are, right? It's pretty easy for us to find what, to find this expression, right? Because we know what x and y are, right? From our previous derivation of how they optimize the payoff. So we don't strictly need the payoff. We just need to find out what x and y are, right? So, yes, and by B I meant obviously the probability of reaching this good state. That's what I meant by B. Okay. So let's take a look at the code. Let's see. Cursor. Fantastic. Okay. So cool. So here's my function, batter payoff. So here are my base cases. If strikes equals 3, return 0. If balls equals 4, return 1. And then otherwise, I use the expression that I wrote above. And then this is the expected payoff, right? This is one of the expected payoffs. Basically, you can calculate this by just, we had an equation, right, where we have left side and right side. So they're supposed to be the same. So I calculated just one of them. Here you can see that, this one is supposed to be equal to this one, right? And when I print it out, indeed, later you can see that these two are, well, this is not the printout, but you can see that they are the same. I have it commented out, right? Okay, so then I have a function for pitch or payoff because, you can do that as well. I just did it just in case, but I did it just to make sure. But it's supposed to be, the pitch or payoff is obviously the exact negative of the batter payoff, right? Finally, here's my reached good function, which is about reaching this good state. So here I found x, here I found y, and then notice again that here, r equals 4. This is the payoff on the home run, and then for the pitcher, it's minus 4, right? So, and then here's that final line that I wrote, right, where it's x times y times b reached plus 1 minus x times y times s reached plus 1 minus y times x times s reached plus 1 minus y x minus 1 minus y 1 minus p times s reached, right? And then finally, the way I actually solve this problem is just very stupidly with a binary search, right? So if you pick 0 and 1 here, you get you get a divide by 0 error. So we don't want that. So I pick 0.0001 and 0.999, and then here I just evaluate different possibilities, and I do a binary search until I find the one that maximizes. So I expected it to be smooth, right? This is why I could do this. Yeah, so until I found that there were 1e minus 15. And so here's what my functions look like. Here I have the pitcher payoff. This is the probability P. And then this is the current number of balls and strikes. So this is like a good way of thinking about the recursive, functions that I defined before. And then we have reach good, 0.500. And I can, change this. So, just to make sure, right? The pitcher payoff, let's say when it's 4, right? This one should be equal to, or -1. I'll do batter payoff right here, right? So this will be equal to 1, right? The batter wins, right? If it's if it's equal to this instead, then we get 0 points, right? But then for anything in between, right? So from 0, the batter payoff is on average, right? 0.919, and the pitcher payoff is exact negative of that, right? And then here, after doing this binary search, this is the exact answer to 10 decimal places, and this matches. If we go back to the, let me see, window capture. If we go back to here. The solution is indeed 0.29 this thing, right? So that's it. Thank you very much for tuning in, and good luck on next month's problems. Thank you.